Okay, so now you know how to draw the Lewis structure and you know how to calculate the, what's it called? Formal charge. Okay, so you know how to do both of those things, right? And now we have to talk about the exceptions to the octet rule, okay? So the octet rule, which you know, says that every atom wants to have 8 electrons, okay? But there are 3 exceptions to this rule because, like most scientific theories, it's wrong as shit, okay? So the 3 exceptions to this are really easy. It's either it's going to have less than 8 atoms, more than 8 atoms, or instead of having a pair, it's just going to have a single atom slapped on there, okay? So I've got 2 examples where this would happen, BeCl2 and BF3, all right? So both of these examples are examples where the octet rule is going to be wrong in the fact that we're going to have less than 8 atoms, all right? And the reason that this is going to be connected to the thing we just practiced, which is formal charge, all right? So let's write out BeCl2 as if we were doing it like any other Lewis structure, all right? We'd go through all the steps. Be has 2 electrons, Cl has 7. We'd figure out how many we have total, how many pairs. We'd realize that Be is the central atom, and then we've got our Cl's on each side, and then we would end up having a structure that looks something like this, okay? So the next thing that we need to do is calculate the, I'm forgetting it again, formal charge, okay? So we're going to calculate the formal charge. We're going to realize Cl is going to be +1. This one's also going to be +1 because it's the exact same. And then the Be is going to be -2. Not the best, all right? We got no zeros, okay? But if we look a step before this, before we added the double bonds, and we look at the, I guess, not octet rule applicable model, which looks like this, we would realize that the charge is 0, 0, 0, all right? And because the formal charge says that this is the perfect layout, it's actually going to be an exception to the octet rule, okay? So essentially, in class, what she's asking for is once you're done making each Lewis structure, check the formal charge and make sure that it isn't better before you balanced the octets, all right? And if it does happen to be a better formal charge, then just use that one, all right? So let's try it with BF3, all right? So if we were to do it the normal way, we'd have our boron, our boron, I don't know, in the center, and then the 3 F's surrounding it. We would have one of them containing a double bond. And then the rest would just have their regular octets. And if we did the number calculations, we would realize that the charges come out to be 0 on the 2 single bond F's, +1 on the double bond, and -1 on the central atom. All right, and that's not that good, because if we look back to our undouble bonded Lewis structure, pretend the electrons are outside of this, like that, we'd realize that they're all zeros. Another example where doing the octet rule applied Lewis structure is actually more realistic to happen in real life, okay? So those are our exceptions to, or that's our first exception to the octet rule. Okay, so we talked about when there's going to be less than 8 electrons on a central atom. Now we're going to talk about when there's going to be more. This is called expanded valence shells, all right? And it can only affect a very specific group of atoms, okay? That group is, I'm going to write it here, non-metals, and it has to be period 3 or higher. All right. So I guess the best practice would be whenever you get a compound and they're like, make a Lewis structure, check your central atom and say like, is it a non-metal? Yeah. Is it period 3 or higher? Yeah. All right, I'm gonna have an expanded shell. Most people probably aren't doing this in our class though. Most people are probably just gonna try to do it the normal way and be like, oh shoot, this ain't working. It's got more than an octet. And so they're just gonna have to restart, okay? So what the teacher told us to do is just check before we make a Lewis structure. Is it a non-metal? Is it period 3 or higher? All right, so let's start with PCl5. All right, our central atom is P. All right, and we have checked and made sure, P is exactly, or it is a non-metal, and it is period 3 or higher. Okay, so we're gonna realize that we can actually bind all 5 of these CLs to the P. All right, and doing the regular Lewis structure calculations, figuring out how many pairs we have, all of that stuff, we are gonna realize that it comes out to be a perfect structure. All right, they're each gonna have their shells filled, each of the external atoms. Our central atom's gonna have more than 8, but that's okay because we just talked about it's a non-metal, it's higher than period 3. And it's going to be a relatively good charge. All right, we're not gonna have super high numbers. We're not gonna have non-electronegatives with negative charges. All right, so let's try this with SF6. If you want to, you can like pause the video and do it on your own or just watch, all right? We're gonna realize S is our central atom. We're gonna look, is S a non-metal? Yes, sulfur is a non-metal. Is it period 3 or higher? It is period 3 exactly. So we can bind all 6 of these guys, of these F atoms, to our sulfur. All right, and then it would end up looking exactly the same with the filled octets on all of the external atoms, and it would work out perfectly just like that. All right, so this octet exception is super easy because all you have to check for is non-metal and is it period 3 or higher, and it saves you a lot of work with balancing electrons. Okay, so last video on the exceptions to the octet rule, right? And this is kind of still talking about the expanded valence shell, and this is also talking about the odd electron, right? So let's start with H2SO, all right? So I'm gonna skip the whole Lewis charge forming part of it, okay? And go straight to the finished product. If you followed the regular way of making this, which you can do, all right? It's not one of the examples like I showed before where you have to expand the central atom just to form it, okay? But it is going to be smarter to do that, which you'll see in the end, okay? So let's say you built it like normal, all right? And you are keeping in mind that sulfur is period 3 or higher and is a, what's the word? Non-metal, okay? So you've done this, all right? Now you need to calculate the formal charge. And you'll realize these H's are zeros, which is nice. These 2 side oxygens are also 0, which is nice. -1 on the bottom and the top, which is less nice. And then a +2 in the center, which is also not as nice. So now you see that you have sulfur, which is period 3 and non-metal, and you're like, hey, I can expand this shell. Is it going to make the formal charge better? Is it going to turn it to all zeros? Let's, I don't know, experiment with this. So we want to add 2 electrons to the central atom while taking an electron away from these two outer oxygens. And we can do that by turning these top oxygens into double bonds. All right? And when we do that, you're going to realize that the charges now become an all-around zero. Okay? So this is the third, or I guess the second scenario where you would want to expand the central valence. All right? Either you can't create the Lewis structure without it, or it's just more likely to happen because the formal charge is more realistic. All right? So that's the end of expanding valence shells. Now we're going to talk about odd electrons. This was talked about very little in class, and I don't know a whole lot about it, but I do know what it means, which is literally just having one electron that isn't paired. All right? So if you were to draw NO2 out, you would end up with something looking like this. All right? You've got an extra valence on the nitrogen. Don't know what this means, don't know what this leads to, but she just wants us to know that this is exactly the same thing as if you instead had the single bond, or the single electron on the outer electron, and then one of the double bonds on the central atom. All right, she just wants us to know that this is the exact same thing. Okay, so that is all of our exceptions. You know when it's going to be less than 8, you know when it's going to be more than 8, and you know that having a spare electron is not going to ruin the entire Lewis structure.